Okay, welcome to lecture. We're going to pick up with the next chapter, which is, where we left off, I think. We finished chapter 8, which was gases last time. So we're going to pick up with chapter 9. Again, these lecture notes are up online in the module section. So we'll pick up here with chapter 9. That will not be on the exam. And again, a reminder, your exam is on Thursday. And it will cover through chapter 8. And again, this will not be on that exam. This will then start what will be on exam number 4, which will shortly be coming up after Thursday in a couple of weeks, I think. As usual, if you do have any questions, please feel free to ask them below in the chat box. And again, we'll stop and go back if we happen to have been past where your question was. All right, so in this chapter, we're going to talk about the liquid state. We're also going to talk a little bit about solids at the end and some issues with liquid involving energy, a little bit, not a lot, but some of the forces that hold liquids together. All right, so the first thing we're going to talk about is kind of the difference between, actually, let me go back here, find a page, this will work. So the first thing we're going to sort of talk about is sort of two different types of forces, and really we're going to focus in on one type of force. And the two different types of forces are what's referred to as intramolecular force. And that's the force within a molecule that holds it together. So for example, if you took, one water molecule, the intramolecular force, which means within the molecule, would be the force that holds together basically the hydrogen to the oxygen and the other hydrogen-oxygen bond, also known as covalent bonding, right? Also, ionic bonding is an intramolecular force. And that's different than what we're going to talk mainly about here coming up, which is intermolecular force. And in an intermolecular force, basically what we're talking about here is the force that holds, say, if you took 2 water molecules or more, and you basically held those together. It's the force that holds basically one molecule together with another. So for example, as we'll talk about, and as we know, water is polar, where the hydrogen is more positive, the oxygen is more negative, hydrogen is more positive, oxygen is more negative in this water. And again, that attractive force between the two. So an intermolecular force is the force that holds, say, 2 molecules together or more. Now, again, intramolecular force, things like, again, ionic bonding, covalent bonding, those are all intramolecular forces. Now, in terms of strength, we do know that between the two, one is much stronger than another. And the one that is much stronger is, as you may be able to figure out, is actually the intramolecular force. So an intramolecular force is always much stronger than any intermolecular force that we're going to talk about. And that is because we know just actually from this example here, so for example, if we had water, and when we get to something like the boiling point with water, right, and we heat up water and we boil water, what happens is water goes from the liquid state to the gas state. And what that means is it's actually this bond here, this intermolecular force, that gets broken first. And we know that's true because what happens when we do heat something at its boiling point, for example, what we get is basically water or steam, which is essentially water in its gas state. And what ends up happening is we do get, a couple of water molecules that are now free from each other in the gas state. And we know that's true because if it was opposite of that, so if it was sort of opposite of that, and the intramolecular force was actually weaker than the intermolecular force, what would happen when you get to something like the boiling point is if it was opposite, this bond here would break and this bond here would break before this bond. And that would be bad news probably if you're trying to make some pasta or something, because then you would have probably just made some oxygen gas and hydrogen gas. And I'm assuming you probably wouldn't get to the pasta part at that point. So again, any intramolecular force is always going to be stronger than any intermolecular force. And then again, that simple example of basically heating water from liquid to gas is an illustration of that, because when we do that, the force that holds the two water molecules is the one that breaks, and you still end up with two intact molecules over here. Again, if it was opposite of that, you would expect it to completely break apart, get like alphabet soup. Everybody would basically fall apart. So ionic bonds, the strongest really here in terms of intramolecular force. That's a very strong electrostatic attraction between the positive and negative, which is really what holds that together. Now, I didn't go back far enough, huh? Oh, well, that's bad. Let me just do this then so we can actually see what's on the screen there. We're just going to, there we go. All right. So when we talk about intermolecular forces, which is mainly what we're going to kind of talk about here in this chapter here, we're not going to really focus too much on the intramolecular forces, but the intermolecular forces, again, as I mentioned, are the attractive forces between molecules. Again, they're responsible for the condensed states of matter like liquids and solids. They're also responsible for pretty much things like boiling points, melting points, freezing points, those type of things. And the strength of these intermolecular forces are really, what's responsible for whether or not we see something that has a higher boiling point than, say, a lower boiling point. The stronger that force is that holds one molecule together with another, the higher the boiling point would be, because again, molecule A here and molecule B that's held together, the stronger that force is between them, you can take more energy to break it. And more energy would really translate to a higher temperature, usually at things like boiling points, melting points, and so forth. Now, a gas, as the temperature is lowered, the molecules, again, no longer have enough energy basically to break apart from each other, and you get that condensation occur when those gas molecules basically can escape one another. So as the gas molecules, again, are flying around, they lose some energy, they sort of slow down, and they're able to kind of clump together and kind of fall into the liquid phase. Obviously, if you continue to take out energy, they will go into the solid phase. Again, they lack that energy to basically break apart from each other to really get them away from those intermolecular forces. So intramolecular forces, as I mentioned, again, are ones that are the forces that hold together really one individual molecule together. They're responsible for the stability of that molecule. And again, that intramolecular forces are things like ionic bonding, covalent bonding. Those are things within the molecule that basically hold it together. And as we talked about, usually those intermolecular forces are going to be much, much weaker than the intramolecular forces. Again, so everybody doesn't really just fall apart as you start heating things at normal boiling points. So what we're going to talk about here and on all these interactions are basically what are intermolecular forces. So these are all intermolecular forces. And as we will essentially see as we go through these intermolecular forces, they all really boil down to a basic interaction. And the basic interaction that occurs is there's a positive side to one molecule and a negative side to the other. So that's that classic interaction of electrostatic interaction, the opposites attract, and pretty much all intermolecular force basically boil down to this basic interaction of the positive side of one molecule will be attracted to the negative side of another. And that attraction is what's going to hold them together. The first type of intermolecular force is one that's referred to as a dipole-dipole force. And you may remember dipole, and you may even remember those dipole arrows that we drew when we talked about bonding, right? And dipole-dipole forces are really the forces that hold together a polar molecule with another polar molecule. Yeah. So that is really the force that holds that together. And if you remember, what makes something a polar molecule when we talked about bonding is, as a whole, that molecule basically will have an unequal sharing of electrons, right? And ultimately what that means is that there is going to be a side that is more positive in that molecule, and there's going to be a side that's more negative in that molecule. And because they both have that positive and negative side, again, that is essentially the area where they're able to basically interact with one another. It gives them a way to basically line up and come together and attract one another. So dipole-dipole, again, is the major intermolecular force that is used by a polar molecule when it wants to interact with another polar molecule. And here's just a basic sort of arrangement here. Again, the negative side of one will attract the positive side of the other. And they do try to, when they all kind of get together. So again, we got to think about these things as not just, oh, there's just two molecules that are going to be together. There's obviously, if you have something, say like water or something of that nature, you don't just have obviously two water molecules in something, right? If you have a glass of water, there's a lot of individual water molecules. So what happens is these guys do try to arrange themselves in a way that will maximize the attractive forces. So that's going to maximize this force up here, our positive and negative attraction, while still minimizing sort of the repulsion type forces. So no matter what happens, sort of in three-dimensional space, you're always going to tend to have some positive sides of molecules near positive sides of molecules, negative sides near negative sides. It's just the way it's going to work out when you get a whole bunch of molecules together. So dipole-dipole, they will kind of move around and sort of orient themselves and try to align themselves in a way where, again, they really do try to maximize that positive negative attraction. So dipole-dipole is, for this situation, polar molecule basically working with another polar molecule. And here's a picture of that. Again, you can see the red is the attractive forces, the blue is sort of the repulsive forces here. And again, no matter what happens, you are going to get some negatives near negatives, some positives near positives. But again, they'll sort of move around and try to orient themselves where they really do try to minimize those areas where you do have sort of negative near negative and positive near positive, and really try to accentuate the attractive forces between the positive and negative side of those molecules. Now, a special type of dipole-dipole interaction is one where what is sometimes referred to as ion dipole interaction. And much like the sort of name implies, it is between an ion, which means it's either a cation, which is positive, are an anion, which is negative. And basically here, it is an ion that has a charge and a polar molecule. So a polar molecule, again, going to have the negative side and the positive side. Polar molecule, PM. And again, that's going to give it the attractive force. Same thing over here. Our negative guy, the polar molecule will line up, but it will line up its positive side near that negative side. And again, going to give it a place to interact with each other. The strength of sort of the force there is based on the charge and size of the ion and the dipole. So the larger, if you remember, if something has a dipole, it has a dipole moment, and those dipole moments could be sort of a small separation of charge, could be a very large dipole moment or separation of charge. And again, depending on the size of the dipole, also the size and charge of the ion will create a stronger charge or stronger attraction. For equal charges, a cation usually will interact stronger than an anion. And you may remember, in order to become a cation, you have to lose electrons. And what happens to your size is gets smaller, right? So the positive guy gets smaller, which means the smaller guy will have probably a stronger attraction to, say, a polar molecule than an anion, which has gained some electrons and become larger. So ionic compounds usually have low solubility in nonpolar solvents, and that is because this is essentially what happens when we take something, for example, like sodium chloride and some water. When the sodium chloride goes into water, it breaks apart into a sodium ion, breaks apart into a chloride ion. And remember, again, water has two sides, the oxygen being more negative, hydrogen being more positive. So again, the negative side of water is going to be attracted to our positive cation, while the positive side here of water will be attracted to the negative anion. And this is what essentially will help something like sodium chloride, for example, dissolve in water, right? All those water molecules basically surround the ions. It allows them to sort of disappear with quotes on it. Again, they don't disappear. They just get mixed up in the water network. And it also prevents the ions from coming back together. Again, when we evaporate off the water, there is nothing in the way of the sodium ion and the chloride ion. And remember, that is an intramolecular force, which means when they can see each other, there's nothing in the way like water. They're going to want to come back together to make that sodium chloride. But here, the water sort of acts as a buffer to keep them apart, not allowing them to come back together and to be able to dissolve. Ionic compounds, when we do put them, again, in something that is a nonpolar. So again, a reminder that nonpolar basically means no charge, right? It is something that has an equal sort of distribution overall of electrons. So in a nonpolar molecule, there really is not a positive side. There's not a negative side. And because this nonpolar molecule, say down here, lacks a positive or negative side, it has no good way to try to interact with either one of these guys, because again, what the sodium chloride is going to be looking for is something with an opposite charge. And if you try to bring a nonpolar molecule into the mix, it pretty much has no long way to interact with it. And that's why we typically would see, for example, it wouldn't dissolve in it. So if you put something like sodium chloride in there, it would still stay together, because the attractive forces between these two guys are going to be much stronger than the barely any type of force that would exist between, say, a nonpolar molecule and those ions. Any questions on that so far? So what does a nonpolar molecule sort of do? Well, there's a couple of different sort of ways that it can interact. Oops. And one way specifically that nonpolar molecules basically are able to interact with other nonpolar molecules is through what are known as dispersion forces. So basically, this is our nonpolar and nonpolar molecules. This is basically how they both interact with each other, is through what is referred to as dispersion forces. And dispersion forces are essentially the weakest of all the intermolecular forces, because essentially they are these sort of temporary forces that basically occur. And they can be occurred by two different methods. There's a couple of different methods by which, you could kind of temporarily make these things happen. And this is what is sometimes referred to as an induced dipole. And an induced dipole is basically the separation of the positive and negative charge in a nonpolar molecule or a neutral molecule caused by the presence of an ion or a polar molecule. So one way is you could get an ion-induced dipole interaction. And in an ion-induced dipole interaction, like what we see over here, in our neutral, our nonpolar molecule, if we happen to put a positive ion next to it in this normally neutral molecule, temporarily what's going to happen is the electrons in this molecule will all head to the left-hand side, right? Because they're negatively charged. So they're going to be attracted to the positive ions, which means this neutral atom here that normally has no charge, no positive or negative side, will temporarily gain a positive and negative side. And that's what is known as being induced dipole, because it normally doesn't have it, but just because of this presence of this ion being there, it temporarily has this positive negative side. And at that moment, it temporarily gets away to basically interact with each other for a little bit. Another way you could do that is with a polar molecule, which is what we got going on over here. And in a polar molecule, same idea. If you put a polar molecule next to, I'll just draw it on this side, very badly drawn, next to a nonpolar molecule. If this happened to be my negative side here of this even worsely drawn molecule here, the electrons in this case would actually go away from that side, and again creating a positive side over here. And again, you will get this temporary sort of attractive force that will happen. And that is what is sometimes referred to as a dipole-induced dipole interaction. This is also why when you take something, for example, like oil and vinegar salad dressing, right? You can mix it. And, it will stay mixed for a short period of time, right? Because it's able to do some of this interaction here. The oil, by the way, is nonpolar, is pretty much all carbons and hydrogens. The vinegar is basically acetic acid, which has a polar side. So for the short sort of term, when you do that and kind of mix the salad dressing, it does mix, right? And when you put it down the bottle, the salad dressing, what you end up seeing is eventually everybody will separate out from each other. And basically, that's the same idea here. Over the short period of time, these molecules, when you try to mix something that's, say, polar or ionic, for example, with something that's nonpolar, for the short period of time, they do have a little bit of ways to interact with each other. Because in reality, everybody, polar molecules, nonpolar molecules, pretty much everybody has the ability to do a little bit of dispersion forces. But it is a temporary sort of interaction. It is nothing that can be sustained for the long period of time. And that's why, again, it's really the weakest of the intermolecular forces. Any questions on that there? Another way that we could kind of do a dispersion force and how nonpolar molecules, for example, nonpolar molecules interact with other nonpolar molecules is by this idea of what is sometimes referred to as polarizability. And polarizability is basically the ease at which you can basically distort the electrons that are in a molecule. So a common way that nonpolar molecules can interact with other nonpolar molecules. So for example, if you have two nonpolar molecules, NP, they are both essentially neutral. They both essentially do not have any charge because as a whole, they're considered to have equal sharing of those electrons. But remember that these electrons are basically moving around, and there is a chance that you can get a distorted sort of distribution. So basically what could happen is, for example, all the electrons here decide we're all going to go take a vacation over here on the left-hand side of this particular molecule. Now, if all the electrons decided to kind of move over there to the left-hand side of the molecule, this normally nonpolar molecule that has no separation of charge will temporarily gain a separation of charge. That's negative on the left and positive on the right. And if this normally nonpolar molecule that has this temporary charge now gains this temporary charge, the electrons in this other nonpolar molecule will decide, whoa, that's a positive side, right? So I want to go this way now. And the second sort of nonpolar molecule that also normally does not have a charge will also gain a temporary charge. And now these two guys that started out essentially not having any type of charge because they're nonpolar gains what is referred to as sort of a instantaneous dipole. Yeah. And basically they now have a place where the positive side of one would be attracted to the negative side of another, and they have a way to basically interact with each other. These are really temporary type forces because, you know, as soon as the electrons decide in this same molecule here, we're all going to kind of go back the other way. It will break apart. This guy will have some other interactions. They'll break apart. They'll make some new interactions and so forth. So another sort of dispersion force, and really sort of the way that a nonpolar molecule basically behaves with another nonpolar molecule, is through what is referred to as dispersion forces. And a lot of times this happens and it gains this sort of instantaneous dipole, which again is relatively on the weak side, because as soon as those electrons sort of move back, you know, they're going to undo sort of that interaction, make new interactions, undo, make new interactions. Now, in terms of if you're trying to compare, you know, the strength of this dispersion force, and you have two, say, nonpolar molecules, and you want to know this nonpolar molecule with itself, our nonpolar molecule number 2 over here, you know, which one would perhaps have the higher boiling point? And you can make that sort of comparison because the strength of something like dispersion forces actually increase with molar mass. So the idea here is, let's say that this guy over here, the molar mass is 90. The molar mass of this guy on the left, we'll say, is 20. So the idea here is the greater the molar mass, or the more molecules that something has, the more atoms that something has, right? The only way you typically would get a higher molar mass is more atoms. More atoms would mean more electrons. More electrons means a greater opportunity for those electrons basically to kind of all fly to one side of the molecule than the other. And that usually leads to a stronger dispersion force sort of interaction. So if you're trying to compare, again, two nonpolar molecules and trying to figure out which one may have a stronger interaction with itself and thus a stronger boiling point, The higher the molar mass, the more atoms, the more electrons, the greater the opportunity of that sort of polarizability to occur, where those electrons basically will be distorted. Any questions on that there? Now, the attractive forces that arise as a result of these temporary dipoles induced in an atom or molecule, again, are called dispersion forces. And as I mentioned, dispersion forces, usually the strength of them will increase with molar mass. And as I mentioned, the larger the molecules are more electrons. And don't forget, the larger the molecules, like it mentions here, those outer electrons are a little bit further away from the nucleus, so they're not going to be held as tightly, which means, again, there's sort of a greater chance of those electrons basically moving around. All these sort of intermolecular forces are, again, sometimes referred to as van der Waals forces. And here's sort of an example of that instantaneous dipole. Again, a normally nonpolar molecule here first gets a charge because those electrons sort of moved, creates a positive side in this molecule. That's going to create the electrons in this molecule to head over to the left. And now again, this molecule on the left and molecule on the right, normally that don't have charges, now have a positive side and a negative side. And again, it gives them a place to interact with one another. Now, the last type of intermolecular force, which is a special type of intermolecular force, hydrogen bonding, is really part of dipole-dipole interaction. But it is a class of intermolecular force sort of by itself as well. So we do use hydrogen bonding as sort of its own class of ways to describe intermolecular forces, although it is typically kind of under really the big umbrella dipole-dipole. Hydrogen bonding is a bond, much like the name implies. It is a bond between hydrogen and an electronegative atom like nitrogen, oxygen, or fluorine. And if you look on the periodic table there, that is right about in this region, your upper right of the periodic table. And what we know about the upper right of the periodic table, that is more electronegative, right? And those are very, very electronegative atoms, right? With fluorine being our most electronegative, which means when we hook up a hydrogen to an oxygen, a hydrogen to a nitrogen, and obviously a hydrogen to a fluorine, we are definitely going to create a pretty polar bond where the hydrogens will all be partially positive. Everybody on this side here will be partially negative, in that particular bond. So that's the first thing. And that's the important thing, is just because something has hydrogen in it does not give it the ability to hydrogen bond. It does need to be one of those types of bonds. So hydrogen bonding is what we see with water and another water molecule, for example. Again, the water molecule being more negative here on the oxygen, more positive here. And when it hooks together with another water molecule, we get our hydrogen bonding to occur. By the way, these interactions don't necessarily always have to be with themselves, although a lot of times they may be. If we took something like water and this guy here, which is methanol, methyl alcohol, although this part of the molecule is nonpolar, this part is polar. This can be more positive. This guy is going to be more negative. Same thing on our water. And again, we're going to have that hydrogen bonding between the hydrogen, the oxygen, and one molecule. So these intermolecular forces, and it's a good point to sort of bring up as well, these intermolecular forces, when we talk about sort of things like boiling points, melting points, and the effect that it has on things like boiling points and melting points. What we're really talking about is sort of this interaction like we have over here, where we have basically the same molecule interacting with itself, basically water interacting with itself. And that would increase the boiling point of water, for example, because of the hydrogen bonding that occurs. When we talk about how one molecule can interact with another molecule, probably outside of sort of boiling points, again, this would be more so what's happening here. So sometimes people think that the intermolecular force is always either, sometimes people think it has to involve always the same molecule with itself, which it can, but it doesn't have to. Or sometimes people think about intermolecular forces that it always got to be necessarily two different molecules interacting, which it does not have to, but it can be basically both of those cases when we talk about intermolecular forces. Same thing, for example, if I take something like ammonia. Ammonia here, again, a hydrogen connected to a nitrogen. This is going to create a polar bond, able to hydrogen bond as well. Again, the nitrogen to the hydrogen, nitrogen being more negative here, and hydrogen being more positive. So let's take a look at this guy here. The question is, can it hydrogen bond? So think about it here and think if you think it can hydrogen bond or not. So the question does really lie in sort of what type of molecule we're dealing with. So when we look at this molecule, the first thing you want to think about is, well, it's got, hydrogens all over the place. That seems like a good thing for hydrogen bonding to actually have hydrogens. But there's a couple of problems sort of with these hydrogens. First off, when we look at this molecule here, it's actually a non-polar molecule. So if you remember, a couple ways you could come to that conclusion. The first way is the bond between carbon and hydrogen itself is non-polar. And that technically means all the way through there, all those bonds are non-polar, which means there's no separation of charge. And that also means that in order to normally have a polar molecule, you need some type of polar bonds. So even if you look at it and go, well, there's still a slight difference between the carbon and the hydrogen in terms of electronegativity. And you would be right. Perhaps you remember that if you take the carbon and the hydrogen, you get a difference in electronegativity of about 0.4. So that 0.4 is the cutoff for the non-polar bond, but it does tell you that it isn't being shared truly perfectly equal in one another. But when we look at the geometry of this molecule, it is 4 electron pairs and 4 bonds. That is your tetrahedral geometry. And that again is a symmetrical geometry, which means that although even if you consider it to have a slightly little polarness happening there, the geometry would make those dipoles essentially cancel each other out because everything is attached. So although CH4 has a ton of hydrogens there, not a one of those hydrogens can participate in hydrogen bonding. So this is a really good example of just because you see hydrogens there, it really cannot participate in hydrogen bonding. You really do need this combination to allow it to happen. You need a bond between hydrogen and a nitrogen, oxygen, or fluorine. Like what we have here with water, we have an oxygen bonded to a hydrogen, right? Like what we have here with our NH3. We have a hydrogen that's bonded to a nitrogen. And here we don't have that. We do have the hydrogen part, but we don't have that electronegative atom that's necessary to basically make that bond a polar bond, right? So there's no separation of charge that's going to happen here. So if CH4, even with all those hydrogens, cannot hydrogen bond, what can it do? Well, since it's a nonpolar molecule, we know that it will be using dispersion forces. Yeah. So our CH4 will be basically using dispersion forces as its main source of intermolecular forces, again, because that is the only way it can sort of maintain any type of interaction that's going to occur. Any questions on that? All right, so here's our example of some hydrogen bonding occurring in each of these. So to summarize sort of the three sort of different types of intermolecular forces that we sort of talked about, along with the little sort of individual categories, on one end we have hydrogen bonding, which is what's pictured on this slide. In the middle, we sort of have dipole-dipole. And on the other end, we basically have dispersion forces. So when we talk about hydrogen bonding, this is typically the strongest bond in terms of intermolecular forces. Dispersion forces is the weakest out of all those. And again here, in terms of who uses what for the most part, hydrogen bonding is typically for polar molecules that interact with other polar molecules. But the difference here is that they have the ability to hydrogen bond, which means, again, they have a hydrogen that is bonded to a nitrogen, oxygen, or fluorine. Well, dipole-dipole, which includes ion dipole that we talked about as well, is the strongest intermolecular force for polar and polar molecules that do not have the ability to hydrogen bond. So again, that's sort of the, although they are sort of almost the same deal, that is sort of the difference between these two. Dipole-dipole is usually reserved for polar molecules interacting either with themselves or polar molecules interacting with other polar molecules with the lack of ability to hydrogen bond. While hydrogen bonding is polar molecules interacting with polar molecules that have the ability to hydrogen bond. And the weakest out of all of these is our dispersion forces, which includes instantaneous dipole, induced dipole, those temporary type forces. That is the major force that holds a nonpolar molecule together with another nonpolar molecule. So again, these are those more temporary forces and the weakest out of all of them and the strongest. So when we talk about things like boiling points, melting points, those guys that have the ability to hydrogen bond will have the highest of those guys. Those guys that pretty much are your dispersion forces will have the lowest in terms of those. And your dipole-dipole will sort of fall in between in terms of that. Any questions on the difference between those intermolecular forces? And just to also clarify, really the difference between, say, hydrogen bonding or dipole-dipole and dispersion forces, you may say, well, they're all sort of that positive negative interaction. Why is, say, this guy over here so much weaker than, say, a dipole-dipole interaction, even though they're both basically the same positive negative attraction? And the answer lies with the actual molecules themselves. A polar molecule versus a nonpolar molecule. In a nonpolar molecule, it is basically neutral, right? No separation of charge. In a polar molecule, it has that separation of charge. And the main difference between these two, the dipole-dipole and dispersion forces, for example, and what makes the dispersion forces so weak is, in order for this nonpolar molecule to interact, it needs something to happen. It needs those electrons to move. It needs something to come near it that has a charge. It needs some help to get that charge to occur. And the difference is, though, a polar molecule, something like water, for example, no matter what the situation is, it's always going to have a side that's positive. It's always going to have a side that's negative. It's sort of fixed in that sense. Nothing's going to change that. Water molecule moving around will always have a positive side, negative side. Those polar molecules always have a fixed dipole moment, which basically means, again, they have that dipole moment, which means they always have a side that's positive, negative, which means they're essentially good to go. They don't have to wait for anything to happen to interact with each other. They have that positive, negative side ready to go, as opposed to our nonpolar molecule needs a little help to get there, basically. And the problem with the nonpolar molecule is once it gets there, it may not stay there because those electrons may move around and sort of break apart those interactions. Any questions on intermolecular forces before we kind of continue on? Okay, so then we're going to talk about some liquid state and some things that we see in liquid and things that occur with liquids. Liquid molecules, as we know, they're still relatively close to one another, right, when they're in there. There is obviously a little bit more room for movement. Definitely a lot closer together than the gas phase where they're flying around. They have more room and movement, a little bit more energy that they can kind of still move past each other, which is why when we think about liquids, we think about them as sort of fluids, right? They can pour. And they remain in motion and are hard to compress, right? If you ever try to squeeze down on a liquid, it makes a mess, right? And that's because they can apply pressure equally in all directions, as opposed to a gas, which you can't compress down as it's flying around. And viscosity is basically the resistance of a liquid to flow and is related to the intermolecular forces. So water has a low viscosity and motor oil has a high viscosity. And that is because, again, with water molecules, it's going to be using hydrogen bonding. Sorry, a moment there. We'll be using hydrogen bonding. Again, it has that ability to hydrogen bond. Motor oil, which is essentially all carbons and hydrogens, is going to be using dispersion forces, which is relatively sort of weak, and it will have a high viscosity, which is that resistance of a liquid to flow, as like motor oil, right? If you pour it versus, say, obviously liquid water, which has a stronger intermolecular force and thus doesn't have that much resistance to flow. So let's talk a little bit about water and some of the properties of water. A couple of types of forces that are important, and we'll see a little bit later on as well, is cohesive forces. And cohesive forces are the attractive forces between molecules of a single substance. So, for example, the hydrogen bonding that we see in water, the attractive forces between one water molecule and itself. Adhesive forces are the attractive forces between two different water molecules. So as we will see a little bit later, this is basically what results in like that meniscus that we see, right? The reason we see that meniscus, as we'll talk about in a little bit here, is these type of forces as to whether the cohesive forces are larger than the adhesive forces. And in certain cases, this causes things like the curvature of liquid that we see in a glass container. Surface tension is the elastic tension that's found at the surface of a liquid, and a lot of energy is needed to sort of expand the surface liquid. So it is higher for liquids with greater intermolecular forces, and water has hydrogen bonding, which is sort of the strongest intermolecular force. And that means those attractive forces are really going to pull the surface of the liquid. So as we'll see in the picture in just a second, when we have all these water molecules on the surface, as opposed to say some water molecules below the surface, those guys at the surface are really only being pulled kind of to the left, kind of pulled to the right, kind of pulled down. There's nothing kind of pulling them above, which again stretches the surface of the liquid. And again, an example, you could lay like a paperclip carefully on water, and it could kind of sit there. Surface tension in water is a lot greater than other sort of substances, again, because that hydrogen bonding is a very strong intermolecular force, and it's held together very tightly. Kind of like when you pour your soda in your cup, right, or a liquid, right, and all of a sudden you look and it's like, cool, I'm like above the cup's top, and then you go kind of move your hand, you break that surface tension, and then it kind of splatters everywhere. Here's a much better picture of that. But again, here when we're at the surface of the liquid over here, our water molecules here being pulled down, being pulled to the left and right. And again, that's really just going to kind of stretch that surface and make that surface really more sort of tense and tighter, as opposed to underneath, if we were looking at this water molecule here, not maybe perfectly drawn here, but kind of evenly filling pull in every direction. So it's not going to really stretch that water molecule as what you see in the surface, again, because the surface is lacking any type of interaction above it. So instead, it just gets kind of stretched out. And, soap, for example, when we add soap or detergent, the surface tension is greatly reduced in something like water. And basically what soap is it's a long chain of carbons and hydrogens. Even longer than obviously I'm drawing here. And actually it just kind of goes and goes and goes. And at one end, it also has sort of this group here, which is kind of like a carboxylic acid. It's an organic group. And this part of soap is polar. The back part of soap, which is sometimes referred to as the tail, is nonpolar. And the front part, which is the head, is polar. And that works really well for something like soap, for example. That's how soap sort of works. Most dirt is nonpolar. So the nonpolar side of soap basically interacts with the dirt, kind of traps it in there. And then typically when we use soap, right, we usually will wash it off with something like water, which is polar. And thus, when you wash out the soap with the water, you basically will have the dirt going out basically with the water. So it basically kind of traps the dirt. And then you got all this soap basically around it. But on the outside is the part that all likes water basically. So again, when you wash with water, which is polar, it mixes with the outside part, and obviously the dirt goes out with it. Now, when you do put soap in water, right, which is why we usually will kind of wet your car. When you typically put water on your car, or it rains and your car has, for example, wax on it or so forth, or something like an umbrella, typically what you'll see with the water is it will typically bead, right? You'll see all these beads of water basically on it. And again, that's because of the sort of strong interaction between water molecules in itself, those hydrogen bonding. It's not able to basically spread out. When you do put something like soap on, which is again why we usually will wet the car first, right, and then soap it up to kind of spread everything out. It basically, as this picture sort of shows, these are the soap molecules. The soap molecules basically gets in the way of all those water molecules and their ability to sort of hydrogen bond with each other. And what that does is sort of spread out basically, the water molecules. And, there used to be an old commercial on TV about, kind of dishwashing soap, and it had a kind of grease and everything in there. You put like a drop of it in there and you can see like the grease and everything just kind of spread out. I think it's Dawn or something like that. And that's sort of the same idea. When you add that soap, again, it's able to allow everything to spread out because it basically disrupts, the ability of these guys to hydrogen bond with each other. And that's going to prevent the water from making that really tight surface tension that we saw in the previous slide, and going to allow the water basically to sort of spread out. So when we talk about adhesive and cohesive forces, as I mentioned before, it does play an effect on things like the meniscus that we see. And remember, the meniscus is that curvature of the liquid that we see in a glass container. And remember, we read from the bottom of the meniscus. And when a glass tube with a small diameter is basically put into water, the water will rise due to capillary action. And the water forms hydrogen bondings with the oxygen, which is basically on the walls of the tube. So if you take a capillary tube basically a lot of times sealed at one side, kind of open at the other. And again, if you kind of put that in there, you'll see kind of the liquid getting drawn up, into the tube. And the reason we sort of see this curvature upwards in the case of water, we'll exaggerate it here, is the attractive forces between the water and the walls of the container are stronger than the attractive forces of the water with itself. So what we're talking about here, if we go back real quick, just to take a peek at it, where was that? Right here. That is what we're talking about here, adhesive forces, yeah. So the adhesive forces, the attraction between the water molecule and the walls of the container are stronger than the cohesive forces that we were talking about earlier, which is the attraction between the water molecule and itself. So because of that, we do see that curvature of the liquid upwards. Now, that's not always the case. So here with our adhesive forces are greater than our cohesive here. And the opposite is true here. When you take something like mercury, the meniscus actually goes the other way, kind of in on itself. And it's going in on itself because the attractive forces between mercury and mercury is greater than the attractive force between mercury and the glass tube, I guess. And that causes the meniscus to actually bend the opposite way. And if you read it, you do the same thing. You actually read the top of the meniscus in that case. And that is what we typically would see with something like mercury. So again, on the right-hand side there, the cohesive forces, the attractive forces for the molecule to itself, is greater than the adhesive forces between, say, mercury and the container. Any questions on that there? Okay. So then let's talk a little bit about vapor pressure. And vapor pressure has to do with the pressure of the gas above a liquid surface. And just to start off with, the tendency basically of a liquid to vaporize is called its volatility. So if you have a volatile liquid, that means that it can go into the gas phase relatively easy. So it's able to basically escape into the gas phase relatively easy. You usually will use something that's volatile, say in a fume hood, so you don't breathe that in. A lot of times they are flammable, so they don't catch on fire and stuff like that. I almost want to say it was part of that safety video we watched way back when. When we have a liquid in an open container, it will evaporate completely because basically the air will diffuse away those gas molecules. That's why when we have like a puddle, for example, of water, say on the bench top, what's going to happen at the surface of any liquid, nice liquid drawing there. At the surface of any liquid, what's always happening is the equilibrium between those liquid molecules that gain enough energy to escape and go into the gas phase, and those gas molecules that lose enough energy and basically go back into the liquid phase. And at some point that will come to equilibrium, but at the surface of any liquid, you essentially have that process occurring. You got guys jumping out of the liquid phase, you got guys coming back into the liquid phase. And sort of the process of evaporation kind of occurs because, again, as these guys sort of jump out of the liquid phase, potentially if it's an open container, you got air molecules that will push those gas molecules basically away. And as those molecules that escape the liquid get pushed away, they're no longer available to basically drop back into the liquid phase. And eventually it will evaporate. And that's why when we have, say, a little bit of water on the bench top, we have a greater surface area where you have all these sort of guys jumping out into the gas phase all over. And again, you have a lot of air because it's open, obviously, to the environment, pushing all these guys away. And eventually, right, what happens, right, is it gets smaller, smaller, smaller. And then eventually, right, the little puddle of water that was maybe on your bench top there basically will evaporate away. Also, same thing would happen if you just, like it said, had a container that was open, right? It would probably take a little bit longer, obviously, for this to evaporate, right? Because there's a lot of water molecules that really can't get to the surface easily, as opposed to over here where the liquid is pretty much spread out and everybody has the chance to sort of escape at once. And the rate of evaporation would be a little bit slower in that open container. But eventually, if you leave it long enough, it will probably get there, or most of it will probably evaporate away. But as this process is occurring, when we have, at to say, the surface of a liquid, these guys that are constantly jumping out of the liquid phase into the gas phase and vice versa, we gain basically what is known as the vapor pressure, because in this sort of container, we will get some gas molecules that are above the liquid. And thus, if we have gas molecules above the liquid, that means that we will have more pressure, right? Because pressure is associated with gas molecules. So the greater the pressure above the liquid, the more gas molecules we should have. And that would also mean that liquids with high vapor pressures would be said to be volatile. They evaporate really rapidly. Again, that's because of what we were just talking about. The only way to achieve a high vapor pressure means that you have to have a lot of gas molecules, and those gas molecules had to come from the liquid. And that means that they're pretty easily going to be able to kind of jump into the gas phase, and thus they would evaporate very, very quickly because, again, they're very easily able to escape. And as they escape, they no longer will be available to come back into the liquid phase and start to evaporate. Now, the vapor pressure of a liquid at a given temperature is determined by the intermolecular forces. So the larger the intermolecular forces, the lower the vapor pressure. So that means that the stronger the intermolecular force, the lower the vapor pressure. And that is because the stronger the forces are in here, I'll just draw this as a scribble. that are holding these liquid molecules together, the less of them that will be able to get out. Yeah. And the stronger they're held together, the less likely that those guys will be able to escape the liquid phase. And thus, when they escape the liquid phase, there's going to be less gas molecules above the liquid. And less gas molecules would mean lower pressure and a lower vapor pressure. Something that has weak intermolecular forces, something that is using dispersion forces, will probably have a very high vapor pressure. And if you ever done anything with organic chemistry or eventually take organic chemistry, you will see that a lot of organic molecules, which are essentially all kinds of carbons and hydrogens together, they are oftentimes very volatile. And that's because the best that they could do in a lot of cases is, not 100% of the time, but most of the time, the best that they could do is those dispersion forces, which are relatively weak forces that are holding one molecule together with another, which means they're easily able to kind of head out of the liquid part and into the gas part because they're not being held as tightly. Any question on that there? And that's sort of what we see if you take now a liquid, for example, in a closed container, a liquid in a closed container. When you first kind of close the liquid in this container, you have a certain sort of volume of the liquid. And what's going to first happen is, as we can see here in this container, the rate of evaporation will basically start and be high. Now, what's going to happen is these guys are going to start to evaporate, but the problem here is they got nowhere to go because you put a lid on the container, right? So eventually these guys, some of them are going to slow back down. And what you're going to have is, because unlike in an open container like we were talking about on the previous slide, these guys have really nowhere to escape. So you're going to get some guys heading back in the other direction here. And you're going to get some guys that are going to drop back down into the liquid phase. And at some point, the rate of evaporation will equal the rate of condensation, right? Which is the process where it goes from gas back to liquid. And that is when the system basically will reach equilibrium. And typically what you'll see is the volume level will go down a little bit from where it started. And that's the process of when it reaches equilibrium, you're overall going to perhaps lose a little bit of that liquid that you had to begin with. Because at the beginning of this process, when you put it in that container and shut the lid, you have a greater rate of evaporation. But at some point, there won't be enough of those molecules being able to come back into the solution. And the net of what you will typically see is there'll be a little bit of a drop basically in the liquid layer. Any questions on that? Now we could actually sort of calculate the pressure and the vapor pressure here. And that is the delta H of vaporization is what that is. That's the enthalpy of vaporization. Or it's sometimes referred to as the heat of vaporization. And this is the vapor pressure at one temperature. And the vapor pressure at another temperature. This R is the R that has to do with energy, 8.314 joules per Kelvin per mole. These are the two temperatures over here that also does need to be in Kelvin. And we could use this to calculate things like the vapor pressure of a temperature if we maybe change the temperature of a substance. So let's take a look at a problem where we might use this. So here we want to, the vapor pressure of water at 25 degrees Celsius is 23 torr. And the heat of vaporization is 43.9 at 25 degrees Celsius. Calculate the vapor pressure of water at 65. So we could use that formula that we saw on the previous page, the natural log of the pressure at T1 over the pressure at T2. And that's going to equal our delta H of vaporization over R and 1 over T2 minus 1 over T1. So we do need to do a couple of conversions. These temperatures do need to be in Kelvin. So our T1 is 25 plus 273. That's going to give us 298 Kelvin. Our T2 is 65 plus a 273. And that will get you a 338 Kelvin. Let's see here. R is a constant. We have our delta H of vaporization. And we have the vapor pressure at 25 degrees is 23.8 torr. So if we put this in, the natural log of our P1, which we'll call 23.8 over our P at T2, equals our delta H 43.9. I am going to multiply it by 1,000. And the reason I'm multiplying it by 1,000 is because R is 8.314 joules per Kelvin per mole. If you leave this in kilojoules and the bottom guy's in joules, you will be off by a factor of 1,000. So you could convert the kilojoules into joules. You can convert the joules into kilojoules, but you do need to do a conversion usually between these two numbers. Again, because the top guy is usually in kilojoules, bottom guy is obviously in joules as well. So you want to make sure you watch out for that. 1 over T2, which is 338, minus 1 over our T1, which is 298. And I'm hoping that's the number you get there. Let's see here. So if we kind of clean up the right-hand side, 1 divided by 338 minus 1 divided by 298. We're going to times it by 43.9 times 1,000 and divide it by 8.314. And if we do that, we get the natural log of 23.8 over PT2 equals minus 2.0969. To get rid of the natural log, we need to take the E of both sides. So you need to take that E of both sides there and drop a different color in so we can maybe see it. So basically we would take E to this guy and we would take E to this guy here. When we do on the left-hand side, it just becomes 23.8 over the vapor pressure. When we take the E of the other side, we end up with point, it looks like 1228. We're going to multiply the PT to the other side, and that's going to give us, divide the other guy over. Basically, we're going to get this here. And it looks like it does, so it will eventually get to our number that is here. Any question on that calculation? So that's what sometimes referred to as the Claisen-Clapeyron equation, and you can use it to calculate the vapor pressure. You know, again, if you change the vapor pressure, you change the temperature in each of those. Any questions on any of that calculation? And as you can see, not an ideal gas law or anything like that, so it's okay to leave it in torr. You don't have to convert it into atmospheres or anything like that to use that equation, as you can see. The main thing is, again, in terms of the 1s and the 2s, it really doesn't matter which ones you call 1s or which ones you call 2, as long as you keep the temperature and pressure guys together. the ones that go together. So in this case, the 23.8 went with the 25 degrees Celsius. So I called those ones, but I could have called them both twos. Again, as long as you keep those numbers together. So let's talk about some processes that occur with liquids. Boiling, obviously, when a liquid water basically is heated to a high temperature, you start to see bubbles form. And in those bubbles, they're basically water vapor that's occurring. And those water vapor guys can kind of ride those bubbles to the surface. And that occurs obviously at its normal boiling point. But in order for those guys to really get to the top, a couple things happen. A couple of things you might notice when you do heat a solution. First off, when you put like a Bunsen burner, for example, I remember those, I think. When you put the Bunsen burner underneath the water, you sometimes will see a bunch of badly drawn, probably not green, bunch of little bubbles that form really, really quick. Or if you are boiling water on your stovetop there to cook some pasta, as soon as you kind of hit it with the fire, you'll oftentimes see all these like little bubbles that kind of form. And that's really obviously, as you know, if you touch the water at that point, it's probably not hot at all. And what you're really seeing there is because you increase the temperature really quick, you're oftentimes seeing the CO2 come out. And the CO2, which is a gas, becomes less soluble when you increase the temperature. So what you're really seeing in that kind of quick case when you do that is sort of that gas molecules coming out of the water really quickly. But it's really not until you see when you're boiling something, which as we know takes forever if you're watching, right? It doesn't really happen until you start to see those kind of bigger bubbles really start to form, right? And those bigger bubbles are again basically filled with, in the case of water, steam. And you'll oftentimes see it as well as it's happening. You know, you'll see some bubbles start to make its way up and they kind of pop right before they get to the top. Hopefully they don't go out the side of the container there. You'll see some other bubbles where get maybe pop, right? So it's really not until you see those bubbles really kind of get all the way to the top and then pop that you do have sort of this water boiling. And the way that they could get there is, remember that there is basically atmospheric pressure pushing down, right? So the pressure inside these bubbles needs to be equal to or greater than the atmospheric pressure to allow them basically to get to the top and basically escape. And again, that occurs at the boiling point. So at the boiling point, the liquid pressure and the vapor above the bubbles are again equal to or greater than the atmospheric pressure. And obviously boiling points for solutions depends on a couple of properties. Things like temperature and pressure are important for them. As you know, if you, for example, go to a higher altitude or something like that, the pressure changes, as we talked about in the gas chapter, and you actually could get things to boil at a different temperature than you would if you were, example, at, say, sea level and the pressure that's associated with sea level. So another way is, you know, something like raising the pressure will typically increase the boiling point. And like a pressure cooker here, fine artwork. The tight lid on the pressure cooker holds basically the pressure of the vapor above the water, and that results in sort of an increase in the boiling point. Typically, if you lower the pressure, it decreases the boiling point. So again, because of this high pressure, it takes higher for the boiling point to sort of occur, and it will start to occur, say, instead of 100 degrees Celsius in this pressure cooker, the water will boil at, say, 120 degrees, which is, again, a higher temperature than you would see if you lowered the pressure. So as odd as it may sound, when we talk about things boiling, boiling is actually a cooling process. And one way you could kind of sort of visualize that is with this wonderfully done picture as well. We actually have cooling that's happening out the top of a solution that's boiling while we're heating on the bottom. And the result of heating from the bottom and cooling from the top gives us the thing that people sometimes worry about when they're boiling, especially in the laboratory, and they stick their thermometer in there, and the thermometer only goes to 100 degrees Celsius. And they say, should I be worried that I'm at the boiling point? Will this basically break my thermometer by going way above the 100 degrees Celsius? And what you'll see is if you did boil something, say in the laboratory, and it reaches boiling point, the boiling point, say for water, is 100 degrees Celsius in a perfect condition. That means when you get your water boiling, it will basically maintain 100 degrees Celsius. And the reason for that is as it's boiling, you're basically cooling it out the top. You have these fast moving gas molecules, right? Just taking their energy with them out of the water, which will basically overall cool the water while you're still adding some more heat to the bottom. And that is what allows something, for example, like water, when you get to the boiling point, to basically maintain 100 degrees Celsius. Also, why when you look at those thermometers in our laboratory, they typically don't go much above 100 degrees Celsius in a lot of cases. And that's because it's not necessarily needed, because most of the time you'll be boiling water and you'll be around 100 degrees Celsius, maybe a little bit lower depending on the pressure as well, but it will be able to maintain that. So we get these fast moving water molecules that escape the liquid, and we're kind of replacing them with some more heat on the bottom. And ultimately what you get is almost like an equilibrium process where you're able to basically keep the temperature from changing a lot. Any questions on that there? And I think we will stop. I think we'll stop here then. It's a good place. Let's stop here and talk about a couple of things that's on the horizon. So first off, let's see. On Thursday is our next exam, which again we'll go through chapter 8. So that's gases, and I'm not sure what else now. I almost want to say stoichiometry types of reactions, if I'm not mistaken. That sounds vaguely familiar. So that will be Thursday. You can start the exam during lecture, so we will not have a lecture on Thursday. What I might do, though, is I may record maybe the rest of this lecture and stuff like that and post up online just to keep us on track and everything like that. I haven't decided yet, but I'll try to maybe do that. And that means that also today, after we're done here in just a second or two, the next experiment will be up there, and that will be due. And that's the experiment for this week, which is technically gases. It's experiment 11, which is part 1 and part 2. So the videos for part 1 and part 2 will be posted again as soon as we're done here with lecture. It will also be a formal lab report. It will be due, I believe, a week from Friday, I think, maybe something like that. So you can work on that this week as well. You also have the titration experiment, which hopefully you're working on, which is due at the end of this week on Friday. In terms of both of those experiments, if you need help, if you're not sure about the calculations, you should come to lab, yes. And we will have a lab section. I'll be more than happy to go through the calculations, kind of help you with them and sort of what you are trying to accomplish. That also is a formal lab report, so you do need to have that on Friday as well. And again, it'll be a typed lab report. And I think perhaps this last one here will be experiment 11 will be our last type formal lab report, I think. And then we still have a few more experiments to go, but I think we won't be doing type reports for those. So I think this experiment 11 will conclude that sort of type version of the report. But if you do need help on that, you should come to the lab, and I'll be happy to sort of explain how to do those calculations, help you through those calculations. So again, you don't get them incorrect. And we'll talk about, if you like, as well, the gas experiment that's on tap for this week. Any questions on the experiment? So in terms of, see your question, hang on a sec. Are you talking about the titration experiment? Is that what you're talking about? So in your formal lab report, I'm assuming that's what you're talking about. Again, you do need to include the calculations. You could show the calculations for, say, trial 1 would be sufficient. And you could just do the calculations for the other and fill in the table, if that's what you're asking. So in terms of the sample calculations for the titration experiment, I think you did like 3 trials for each of the parts. If you want to show sort of one sample calculation that kind of takes you through all the stuff that you had to calculate, say for just trial 1, you could do that. And then obviously just do the calculations for the remaining trials and put them in your table. Other questions on that? Okay, so again, if you need help with those, you should come through the lab discussion here. And when it starts, and again, I'll be happy to help you through those calculations. And maybe we'll talk about as well the gas one, what's up on in terms of those sort of calculations as well. Again, in terms of the exam, a reminder that it will be open probably starting around our normal lecture time. Again, you'll have to do the same sort of stuff you've done before. There'll probably be a multiple choice part. There'll be a written part where you have to upload your work and make sure that that work is uploaded within the appropriate amount of time. And you'll have to go through the honesty agreement, sign it. That will open up the exam. And then after you submit the exam, which again, you should only submit the exam once after you've answered all the questions. And a reminder that the questions online need to have answers. They need to have the same answers as the work you showed. You can't do a weird answer online and go magically correctly get the right answer with your work. So you do need to submit it correctly in both places. Otherwise, you will not get credit for those problems. Make sure that you do start the exam around our normal lecture time, and you should not run into any issues in terms of taking the exam. If you start the exam too late, say 10 minutes before the availability date, the availability time is over, the computer will cut you off. Yeah, so it'll cut you off with 10 minutes, and you would only have 10 minutes to take the exam. So if you start at our normal time, that should not be an issue for anybody. But if you for some reason decide to wait and start it really late, you will get cut off, and I will not reopen the exam for you. So make sure you start the appropriate amount of time. And a last friendly reminder, there are different versions, different questions, so don't have the right answers on the wrong version or anything like that, like normal. Any questions on any of that stuff that's coming up and stuff like that? So again, the lab for this week is like it is on the schedule, experiment 11, and it has to do with gases. So you really should be able to do those calculations and work through those calculations. But if you want an overview or if you need some help on that or the titration calculations, do make sure you come to the lab today and get that help. Any questions on anything else? And again, the gas experiment is not up yet until I'm done here, and then I'll go pop it up there and stuff like that. Okay, so if there's no other questions, again, I will probably post maybe the rest of this lecture after I record it sometime towards the end of the week and maybe the weekend when I do get an opportunity maybe to do it. And we'll continue lecturing. So keep an eye out for that as well. And we'll can take a little break now, and then maybe about 7:20, I will open up the lab section. And again, make sure you come through the lab invitation. And if you do have questions, again, I'll be more than happy to answer them for you. All right. Any other questions or anything like that? Okay. I will see you in a bit.